Hi everyone, in this video I'm going to be talking about brainwaves. So let's talk about what brainwaves are specifically. So brainwaves are impulses sent from one group of neurons to another. So if you remember in our previous video, we were talking about neural tracks, right? So what nerve tracks do is they send information from one part of the brain to another. And while they do that, they produce rhythmic oscillation. So in some layman's terms, it's basically impulses. So let's draw it out, right? Let's go back to this one. So, okay. First, let's draw one region of the brain, right? Let's draw this region and say that this is your occipital lobe, right? Sorry for the terrible handwriting. I don't have my pad with me today. And when it's communicating with, say, this is your thalamus, I'm just going to abbreviate it as thal. Okay. When it's communicating, what your in neurons do, right? You know how neurons transmit information. So say this is the axon of the erase that. So say this is the axon of the neuron. Say this is your neuron. These are your little dendrites. Sorry, these are horrible dendrites. And this is your axon. And these are your little myelin sheaths. I'll explain more about this in a future video, but for the basics of it, once the dendrites in the neuron receive information and the cell body, which is this circle, this is the nucleus and this is the cell body, process it, and they make a decision, and if threshold is reached for it to fire, an electrical impulse, so let me draw that in yellow, is sent down the axon into the dendrites, which send it out again. So the point in which it starts, right? So that's called the action potential. So the point in which the action potential starts creates an electrical wave diagram, right? So I'm going to explain this more in a future video, but for the basic of it, first the basic stage of how electrical transmission occurs is first, the neuron begins to fire or it doesn't get activated, then it takes a small dip before getting activated, goes down, and goes into a stage where it doesn't fire for some time and then returns to not being fired again. So when the action potential is initiated is this peak point. And this electrical wave is what brain waves are, right? Because all the neurons in that area will usually fire at the same time during the transmission of the occipital lobe to the thalamus. So say the occipital lobe is transferring the information that in V1 that the line is oriented like this. What all the neurons in one specific region of the occipital lobe will all fire at the same time. And that's what a brainwave is, right? So let's just clear out all the drawings. So let's further understand what these are, right? Okay. So yeah, as I said before, neural oscillations sync activity in the same and communicating brain regions. So notice how these have the brief pattern of electrical waves. So there are four different types of brain waves. First are beta waves. So these are frequencies from 14 to 30 hertz, and it's when your brain is active and stimulated, right? So when your brain is not receiving any input, it doesn't get activated as much. But once it has something called a stimulus, so let's define a stimulus really quickly. Okay. So a stimulus is basically something that your brain has to react to. So something that your brain has to react to, right? So that's what a stimulus is. Let's just move this over here so that There we go. So a stimulus is something your brain has to react to. So neural oscillations only occur, or these beta waves occur when you're focusing on a stimuli. So say when I'm looking at myself in the mirror, that's a stimulus because my brain has to identify what's going on. It has to react to it. Then there's alpha waves. So, okay, sorry. Yeah, there we go. So basically what it is when the brain is relaxed, right? You're awake, but you're not actively responding to stimuli, right? Your eyes are closed. And so basically these usually occur when the frontal and parietal regions of the brain are relaxed. But the beta waves, they occur when the frontal, parietal, and the occipital lobes are active. Then come theta waves. So this is relaxed. It's associated with the relaxed stage before going into sleep, right? So just as you're entering slow wave sleep, this is something we'll cover in future topics. So just as you're entering slow wave sleeps, you're usually going to be in theta sleep, and delta waves are when you're deep in sleep. So basically how you can think about this is alpha and beta waves occur when you're awake. You can see how the frequency. So let's talk a bit about wave frequency. This is a bit of trigonometry here. It's not too complicated. I'm sure it's really simple. So in sorry. Let's undo that really quickly. No. Okay. Since it's already happened, let me just quickly explain. I don't know why it's not annotating right now. Okay, there we go. I think it should be annotating. Oh, that's why. Uh-huh. I just did a mistake. So ignore this part for now, the thalamus, etc. So basically, in a wave, right, you have this. This is described. Let me draw that in a better position. So this is one wave, right? So in trigonometry, there are different types of waves. To me, if this was the starting point, then let's see, it would actually be a cos wave because the starting point is on the axis, but that's not relevant. What the basic terminology you need to know is that the highest point is known as the peak, and it marks what's called the amplitude, right? So the amplitude is the distance from the axis to the topmost point or the bottommost point. So the distance will always say this is 3, right? The amplitude of this wave will be 3, or the peak point that it will reach will be 3, or the lowest point it will reach will be 3, or -3 to be more accurate, but if you take the absolute value. Then there's something called a period, right? So usually in math, what a period is it marks one interval of the highest and the lowest point in the wave, right? So this would technically be one period. And in that, the frequency would be how many times the wave occurs in that one period. So according to electroencephalograms, which is what we're EEGs, say this is a period of 10 seconds, right? In a period of 10 seconds, how many ever times you count those peaks are the number of time is the frequency of the wave. So how often they occur. So let's take a quick look here and compare the frequencies of all of these. That's what these are, right? These 18 to 13 hertz. And so basically what hertz are revolutions or waves per second. So per second, how many times does this occur? So as you can see here, the frequencies of the beta waves are the most frequent out of any one of them, right? Delta, you can barely see peaks. They are very, very spaced out, right? However, in beta waves, they're so close together. So the closer they are together, the higher frequency they have, or the more peaks you see, the more frequent they are. See, in alpha waves, you can pretty distinctly see, and then as theta, they begin to spread out, and in delta, they're like completely spread out. But then the peak points, or how high you have them, the amplitude, height of the peaks are known as the amplitudes, right? So the more frequent your waves are, the less amplitude they have. And there's a reason for that. Let's think about this logically, right? The brain has a certain amount of energy that it can exert. When it's going super duper fast, you can't afford to have large waves because that takes a lot of energy. Think about it this way. If you're bouncing a ball, right? If you're bouncing a ball up and down, it would take you a lot of effort to bounce it up and down really high and go back and catch it and then put a lot of effort to bring it back up again. But if you do it in small waves, you can save a lot of energy, and your brain is always trying to conserve energy, right? So the less effort it takes, the more efficient way there is to do it. It's what it'll do. So the more frequency there is, chances are the amplitude will be lower. However, the less frequencies are, you can see that the amplitude significantly increases in theta and delta waves. See how they're very tall, and in beta waves they're really small. So the hertz for beta are usually 40 to 30. So if you think about that, that means in 1 second your brain will produce 14 to 30 times there will be waves going on. That's super fast, right? Then from 8 to 13 hertz, that's alpha, your brain is relaxed and it's not really responding to stimuli. It's like you're resting your eyes. So just think about the point before you're taking a nap, right? You're not really doing anything, but you're thinking about something. You know how before you're going to sleep and you really just can't go to sleep, you're thinking about the things that were happening today. That's probably what's happening in alpha wave sleep or alpha wave, because you're not necessarily responding to anything right then. You're remembering things, but that's not responding. You're not receiving auditory, visual, or olfactory or taste stimuli. You're just remembering things. That's not necessarily an active stimuli. Then there's some in theta waves, you can see that there's not that many repetitions going on because you're basically going into sleep. When you're going into sleep, your body is really just focusing on consolidating memories and doing all of those things, which don't require rapid response. Your brain can take its time with it. So that's why theta waves requires really slow sleep, and delta wave is really just maintaining your homeostatic, or basically it's really just focusing on repairing your brain, right? So it requires the least amount of energy, which is why your delta waves, you can see that they're very spaced out. There's less frequency. Your brain it's not focusing on actively doing it, but it has high, amplitudes. I'm sorry, I blanked out for 2 seconds. It's doing a lot of work, but it's not responding to active stimuli, which means your brain doesn't have to process quicker. So that's what the concept between amplitude and frequencies are. So then what we know is that alpha in your brain, right? We can measure the electricity in your brain through a unit called millivolts. So alpha and delta waves, which are these two waves, can be measured in the 5 to 10 millivolt range, right? Whereas the beta and theta waves, these two, are usually measured and usually rank among 20 to 200 millivolts, right? So finally, we'll go over, just to revise, a thalamocortical loop, right? So it's a region in the cortex communicating with the thalamus and back, right? So let's assume that, I'm gonna say that if we assume this to be the central sulcus and this to be a little less, okay, let's say that this is somewhere along the temporal lobe. So let's say this is probably maybe around your insular cortex or maybe even your primary auditory cortex. I'll go with, yeah, primary auditory cortex. So just to make sure you understand, when the neurons in this region. So say your primary auditory cortex receives information in. So you're listening to me talking to you right now, right? So say it receives that information. It's going to communicate it with the thalamus so that it can, and say now that you've listened to me, you're trying to take notes, right? So what it's going to do is it's going to take the information from your auditory cortex to the thalamus, which is basically a firing of an electrical impulse. So remember our diagram that we saw of the mountain and lake, kind of? That's what's going on here. And all the neurons in that specific region will fire at the same time that these thalamus neurons will. So they're syncing, right? So if we're going to put it into accurate terms, can you guys guess which type of brain waves are being used or which type of brain waves you'll find in this situation? If you guess beta waves, then you are correct because you're actively responding to a stimulus, right? So then what happens is you go back to the thalamus will send it to the somatosensory cortex to produce with that it'll tell you, okay, I'm sorry, not the somatosensory cortex. Let's assume that this is your motor cortex. It'll send it to your motor cortex because you want to elicit an action, right? You want to elicit the action of taking a note. Then that will, through neural tracts, or it will communicate back to the thalamus and will go through a spinothalamic tract. So basically, spino means spine and thalamic means thalamus. So the spine will communicate with the thalamus to send your hands the signals to take notes. So that's a lot of information, and please feel free to watch the video a few times. I'll also be producing notes on the specific topic, just because sometimes when I explain, I use too many words, and reading it and watching the video again will make a little bit more sense. So I'll be publishing notes and worksheets really soon. And yeah, that's it for today. Thank you so much for watching. Bye-bye. Oh yeah, and if you have any more questions, please feel free to email me at stemwme@gmail.com. The email address will be in the description below. So yeah, thank you so much. Bye bye.